Excavation Trenching Shoring Program, General Company Policy. It is the policy of this company to institute an evacuation trenching shoring program for our construction employees. These guidelines provide safe work practices that are to be followed to minimize the risk for an evacuation emergency to occur. This program has been developed in accordance with the OSHA standards found at 29 CFR 1926-650 subpart P. Evacuation work is one of the most hazardous activities to which the employees of Plaas Incorporated will be exposed. The primary hazard is a cave-in. Even though the actual number of cave-ins is minimal, the results are potentially catastrophic. Plaas Incorporated's goal is to eliminate all excavation-related accidents through a rigorous program of training and enforcement. Although our employees might not perform the actual excavation trenching functions, the employees working on the site as well as employees who will perform work operations in the excavation trench need to be aware of these policies and safe operating procedures. In the event circumstances or conditions are encountered which are not covered in this program, all work within the excavation or trench will cease and not continue until additional controls specific to the unique situation have been instituted. Training and education. All job foremen, competent persons, and employees must understand their responsibilities regarding safety. Before beginning work, all employees will be trained in the recognition or potential hazards and precautions to be taken. This training will include safety requirements and procedures that are expected on the job site. Records of this training must be documented and retained in the Manager of Safety's office of Plaas Incorporated. Once the job gets underway, it is equally important to keep employees informed of any new condition which might arise that could precipitate a cave-in incident in the operation. Specific site-related procedures for handling emergencies will be included in the pre-planning activity. This must include, but not be limited to, rescue operations and local or municipal agencies which provide assistance and the means of notification communication, both internally and externally, in handling an emergency situation. Competent person. The designated competent person should have and be able to demonstrate the following: training, experience, and knowledge of soil analysis, use of protective systems, and requirements of 29 CFR Part 1926 Part Sub P. Ability to detect conditions that could result in cave-ins, failures in protective systems, hazardous atmospheres, and other hazards including those associated with confined spaces. Authority to take prompt corrective measures to eliminate existing and predictable hazards and to stop work when required. The competent person, as a tool to ensure all aspects of excavation trench safety are being addressed, may use the Plaas Incorporated Trench Evacuation Review Daily Excavation Checklist and/or the Soil Analysis Checklist forms. Site excavation trench inspections. Site excavation trench inspection shall be made by a competent person and should be documented. The following guide specifies the frequency and conditions requiring inspections. Daily and before the start of each shift, as dictated by the work being done in the trench, after each rainstorm, after other events that could increase hazards, example, snowstorm, windstorm, thaw, etc. When fissures, tension cracks, slowing, undercutting, water seepage, bulging at the bottom, or other similar conditions occur. When there is a change in the size, location, or placement of the spoil pile. When there is any indication of change of movement in adjacent structures. Soil classification. The types and composition of soil must be identified to determine what protective measures must be undertaken. Types and comparisons such as wet soil, sandy soil, or ground have been previously backfilled and should be considered relatively unstable and deserving of strong support. Strata considered hard rock can sometimes contain faults which make it unstable when disturbed by jackhammer activity or other types of vibrations such as vehicular movement. Therefore, soil should be classified as stable rock and three classifications of soil. Type A soil is a cohesive soil with an unconfirmed compression strength of 1.5 tons per square foot. The maximum allowable slope for excavations less than 20 feet deep is 3/4, 53 degrees. Examples: clay, silty clay, sandy clay, or clay loam. Be cautious on soil that is fissured, subject to vibration, heavy traffic, pile driving, soil that has been previously disturbed, or soil that has been sloped. B. Type B soil is a cohesive with an unconfirmed compression strength greater than 1/2 ton per square foot, but less than 1.5 tons. The maximum allowable slope for excavations less than 20 feet deep is 1:1, 45 degrees. Examples: crushed rock, silty loam, sandy loam, sandy clay loam, previously disturbed soil, and soil that meets the compressive strength of A but is fissured or subject to vibration. Dry rock that is not stable or material that is part of the slope system fits this classification. C. Type C soil is a granular soil with an unconfirmed compressive strength of 1/2 ton per square foot or less. The maximum allowable slope for excavations less than 20 feet deep is 1/2 to 134 degrees. Examples: gravel, sandy, loamy soil, submerged soil, or soil in which water is freely seeping, rock that is unstable, or material that is part of a slope system. Test equipment and methods for evaluating soil type. Many kinds of equipment and methods are used to determine the type of soil prevailing in an area. They are described below. Pocket penetrometer. Penetrometers are direct reading, spring-operated instruments used to determine the unconfirmed compressive strength of saturated cohesive soils. Once pushed into the soil, an indicator sleeve displays the reading. The instrument is calibrated in either tons per square foot, TSF, or kilograms per square centimeter, KPA. However, pentameters have errors ranging in the range of plus or minus 20 to 40%. Chevrons, Tovrin. To determine the unconfirmed compressive strength of the soil with a chevron, the blades of the vane are pressed into the level section of undisturbed soil, and the torsional knob is slowly turned until soil failure occurs. The direct instrument reading must be multiplied by 2 to provide results in tons per square foot, TSF, or kilograms per square centimeter, KPA. Dry strength test. Dry soil that crumbles freely or with moderate pressure into individual grains is granular. Dry soil that falls into clumps that subsequently break into smaller clumps, and with the smaller clumps can be broken only with difficulty, is probably clay in combination with gravel, sand, or silt. If the soil breaks into clumps that do not break into smaller clumps and the soil can be broken only with difficulty, the soil is considered unfissured unless there is visual indication of fissuring. Plasticity or wet thread test. This test is conducted by molding a moist sample of the soil into a ball and attempting to roll it into a thin thread approximately 1/8 inch, 3 millimeters, in diameter, thick by 2 inches, 50 millimeters in length. The soil sample is held by one end. If the sample does not break or tear, the soil is considered cohesive. Visual test. A visual test is a qualitative evaluation of conditions around the site. In a visual test, the entire excavation site is observed, including the soil adjacent to the site and the soil being excavated. If the soil remains in clumps, it is cohesive. If it appears to be coarse-grained, sand, or gravel, it is considered granular. The evaluator also checks for any signs of vibration. During a visual test, the evaluator should check for crack line openings along the failure zone that would indicate tension cracks. Look for existing utilities that would indicate the soil has previously been disturbed, and observe the open side of the excavation for indications of layered geological structuring. The evaluator should also look for signs of bulging, boiling, or slewing, as well as signs of surface water seeping from the sides of the evacuation or from the water table. If there is standing water in the cut, the evaluator should check for quick conditions. In addition, the area adjacent to the excavation should be checked for signs of foundation or other intrusions into the failure zone, and the evaluator should check for surcharging and the spoil distance from the edge of the evacuation. Penetration test. The thumb penetration procedure involves an attempt to press the thumb firmly into the soil in question. If the thumb makes an indentation in the soil only with great difficulty, the soil is probably type A. If the thumb penetrates no further than the length of the thumbnail, it is probably type B soil. If the thumb penetrates the full length of the thumb, it is type C soil. The thumb test is subjective and therefore the least accurate of the three methods. Excavation safety considerations. Each excavation and trenching job presents unique problems. Prior to excavation work activities beginning on a job site, the following items and conditions are to be addressed. Surface and groundwater. The amount of water, either surface or contained within the soil, can affect the cohesiveness of the material. It is imperative that the water table and its extreme fluctuations be previously determined prior to starting the operation. Underground installations. The location of underground installations such as sewer, water, fuel, gas and oil, telephone, and electric lines will be determined before starting the trench or excavation work. It will be the competent person's responsibility to verify response utilities are marked. Hand digging will be required when in close proximity to utilities. Utility and service companies plus local officials will be contacted prior to the job to locate and mark all underground installations. Underground installations shall be protected, supported, or removed to safeguard employees. Climate and weather conditions. Changing weather conditions and climate can drastically alter the conditions encountered in excavation and trenching work. Potentials of change in weather and climate must be considered. These can include precipitation, temperatures, flooding, and the occurrence of any type of extreme weather conditions. Physical location of dig. The nearness, type, and condition of any structures, installations, or operations will be determined prior to starting a job. In the event that a potential for damage to adjacent structures is suspect, additional safeguards and procedures will be initiated to provide utmost protection. Traffic conditions. Through job site observation, the type, volume, and peak hours of traffic flow adjacent to the dig will be determined. The close proximity of passing vehicles can cause vibrations and sudden shock, which could contribute to cave-ins by loosening the soil. General information. In the event these pre-planning activities identify a unique hazard to the job at hand, specific loss prevention procedures will be developed, put in writing, and be included as an addendum to the requirements set forth in this section of the Safety Policy Manual. Spoils placement. Temporary spoil. Temporary spoil must be placed no closer than 2 feet, 0.61 meters, from the surface edge of the excavation, measured from the nearest base of the spoil to the cut. This distance should not be measured from the crown of the spoil deposit. This distance requirement ensures that loose rock or soil from the temporary spoil will not fall on employees in the trench. Spoil should be placed so that it channels rainwater or other runoff water away from the excavation. Spoil should be placed so that it cannot accidentally run, slide, or fall back into the excavation. Permanent spoil. Permanent spoil should be placed some distance from the excavation. Permanent spoil is often created where underpasses are built or utilities are buried. The improper placement of permanent spoil, i.e., insufficient distance from the working excavation, can cause an excavation to be out of compliance with the horizontal to vertical ratio requirement for a particular excavation. This can usually be determined through visual observation. Permanent spoil can change undisturbed soil to disturbed soil and dramatically alter slope requirements. OSHA health and safety considerations. Surface crossing of trenches. Surface crossing of trenches should be discouraged. However, if trenches must be crossed, such crossings are permitted only under the following conditions. Vehicle crossings must be designed by and installed under the supervision of a registered professional engineer. Walkways or bridges must be provided for foot traffic. These structures shall have a safety factor of 4, have a minimum clear width of 20 inches, 0.51 meters, be fitted with standard rails, and extend a minimum of 24 inches, 0.61 meters, past the surface edge of the trench. Ingress and egress. Access to and exit from the trench require. Trenches 4 feet or more in depth should be provided with a fixed means of egress. Spacing between ladders or other means of egress must be such that a worker will not have to travel more than 25 feet laterally to the nearest means of egress. Ladders must be secured and extend a minimum of 36 inches, 0.9 meters, above the landing. Metal ladders should be used with caution, particularly when electric utilities are present. Exposure to vehicles. Procedures to protect employees from being injured or killed by vehicle traffic include providing employees with and requiring them to wear warning vests or other suitable garments marked with or made of reflectorized or highly visible materials, and requiring a designated trained flag person along with signs, signals, and barricades when necessary. Exposure to falling loads. Employees must be protected from loads or objects falling from lifting or digging equipment. Procedures designed to ensure their protection include: employees are not permitted to work under raised loads. Employees are required to stand away from equipment that is being loaded or unloaded. Equipment operators or truck drivers may stay in their equipment during loading and unloading if the equipment is properly equipped with a cab-sided or adequate canopy. Warning systems for mobile equipment. The following steps should be taken to prevent vehicles from accidentally falling into the trench. Barricades must be installed where necessary. Hand or mechanical signals must be used as required. Stop logs must be installed if there is a danger of vehicles falling into the trench. Soil should be graded away from the excavation. This will assist in vehicle control and channeling of runoff water. Hazardous atmosphere in confined spaces. Employees shall not be permitted to work in hazardous and or toxic atmospheres. Such atmospheres include those with less than 19.5% or more than 23.5% oxygen, a combustible gas concentration greater than 20% of the lower flammable limit, and Considerations of hazardous substances that exceed those specified in the threshold limit valves for airborne contaminants established by ACGIH, American Conference of Governmental Industrial Hygienists. All operations involving such atmospheres must be conducted in accordance with OSHA requirements for occupational health and environmental controls. See Subpart D of 29 CFR 1926. For personal protective equipment and for life-saving equipment, see Subpart E 29 CFR 1926. Engineering controls, example ventilation, and respiratory protection may be required. Testing for atmospheric contaminants. Testing should be conducted before employees enter the trench and should be done regularly to ensure that the trench remains safe. The frequency of testing should be increased if equipment is operating in the trench. Testing frequency should be increased if welding, cutting, or burning is done in the trench. Employees required to wear respiratory protection must be trained, fit tested, and enrolled in a respiratory protection program. Some trenches qualify as confined spaces. When this occurs, compliance with the confined space standard is also required. Emergency rescue equipment. Emergency rescue equipment is required when a hazardous atmosphere exists or can reasonably be expected to exist. Requirements are as follows. Respirators must be of the type suitable for that exposure. Employees must be trained in their use and a respirator program must be instituted. Attended at all times, lifelines must be provided when employees enter bell-bottom pier holes, deep confined holes, or similar hazards. Employees who enter confined spaces must be trained. Standing water and water accumulation. Methods for controlling standing water and water accumulation must be provided and should consist of the following if employees are permitted to work in the excavation. Use of special support or shield systems approved by a registered professional engineer. Water removal equipment, i.e. well pointing, used and monitored by a competent person. Safety harness and lifelines used in conformance with 29 CFR 1926-104. Surface water diverted away from the trench. Employees removed from the trench during rainstorms. Trenches carefully inspected by a competent person after each rain and before employees are permitted to re-enter the trench. On-site safety practices. Once excavation or trenching begins, specific safety practices are necessary. This includes daily inspections of the excavation or trenching project to detect hazards and to correct job site situations before cave-ins or other accidents occur performed by the competent person. Safety meetings will be held on at least a weekly schedule by the job foreman. Job foreman will also be responsible for the continuing inspection of the work site, conformance to the personal protective equipment requirements of the job, and the safe performance of work on the project. Federal safety and health standards define a trench as a narrow excavation in which the depth is greater than the width and where the width is not greater than 15 feet. An excavation is any mechanically made cavity or depression in the earth's surface. Applicable safety and health laws require that all excavations employees exposed to danger from moving ground will be protected by a shoring system, sloping of the ground, or some other equivalent means. It is further required that all trenches over 4 feet deep in either hard or compact or soft and unstable soil be sloped, shored, sheeted, braced, or otherwise supported, and that trenches less than 4 feet in depth also be effectively protected when hazardous ground movement may be expected. Protection can be provided to workers in a trench or excavation by sloping the sides of the cut to the angle of repose. This is defined as the greatest angle above the horizontal plane at which a material will lie without sliding. The angle of repose varies with different kinds of soil and must be determined on each individual project or job site. When water conditions exist with silty material or loose boulders, or when the trench is being dug in areas where erosion, deep frost, or slide planes are apparent, the angle of repose must be flattened to provide stability to the material. Number 6, other methods of providing protection to workers in a trench or excavation is by the installation or shoring or sheeting, which can be either tightly placed timber shores, bracing, trench jacks, piles, or other material installed in a manner strong enough to resist the pressure surrounding the excavation. In addition to this on-the-site construction of protection, a prefabricated trench shield, which is the movable structure composed of steel plates welded to a heavy steel frame, may be utilized. Timber, aluminum, or other suitable construction may also be used. Federal standards permit the use of a trench shield as long as protection it provides is equal to or greater than the protection that would be provided by the appropriate shoring system. where personnel are required to enter and work in an excavation. The excavated material must be stored or retained at least 2 feet or more from the edge of the excavation. Where trenches cross gas mains, sewers, or soil saturated with organic material, artificial ventilation may be necessary. When internal combustion engines are used in or near trenches, precautions must be taken against exhaust gases entering the trenches. Whenever a support system is used, it must also always be applied by starting from the top of the trench or excavation and working down. During installation of the shoring, care must be taken to place the cross beams or trench jacks in a true horizontal position and to space them vertically at appropriate intervals. The braces also must be secured to prevent sliding, falling, or kickouts. Prior to opening an excavation, effort will be made to determine whether underground installations, example sewer, telephone, water, fuel, electrical lines, will be encountered, and if so, where such underground installations are located. When the excavation approaches the estimated location of such an installation, the exact location will be determined, and when it is uncovered, proper supports will be provided for the existing installation. Utility companies will be contacted and advised of proposed work prior to the start of actual excavation. Except in hard rock, excavations below the level of the base of footing of any foundation or retaining wall will not be permitted unless the wall is underpinned and all other precautions taken to ensure the stability of the adjacent walls for the protection of employees involved in excavation work or in the vicinity thereof. If the stability of adjoining buildings or walls is endangered by excavation, shoring, or bracing, underpinning will be provided as necessary to ensure their safety. Such shoring, bracing, or underpinning will be inspected daily or more often as conditions warrant by a competent person so that protection is effectively maintained. Excavation stresses and deformations. A number of stresses and deformations can occur in open cut or trench. Examples of these include tension cracks. Tension cracks usually form at the bottom. Do that again. 3-2. Tension cracks. Tension cracks usually form at a horizontal distance from 0.5 to 0.75 times the depth of the trench, measured from the top of the vertical face of the trench. Sliding. Sliding or slowing may occur as a result of tension cracks. Toppling. In addition to sliding, tension cracks may cause toppling. Toppling occurs when the trench's vertical face shears along with the tension crack line and topples into the excavation. Subsidence and bulging. An unsupported excavation can create an unbalanced stress in the soil, which in turn causes subsidence at the surface and bulging of the vertical face of the trench. If uncorrected, this condition can cause face failure and entrapment of workers in the trench. Heaving or squeezing. Bottom heaving or squeezing is caused by a downward pressure created by the weight of adjoining soil. This pressure causes a bulge in the bottom of the cut. Heaving and squeezing can occur even when shoring or shielding has been properly installed. Boiling. Boiling is evidenced by an upward water flow into the bottom of the cut. A high water table is one of the causes of boiling. Boiling produces a quick condition in the bottom of the cut and can occur even when shoring or trenching boxes are used. Unit weight of soils refer to the weight of one unit of a particular soil. The weight of soil varies with types and moisture content. 1 cubic foot of soil can weigh from 110 pounds to 140 pounds or more. 1 cubic meter, 35.3 cubic feet of soil can weigh more than 3,000 pounds. Trench rescue. Scene management. The following steps should be taken if a trench cave-in occurs on the job. The information in these steps will need to be relayed to the fire department and others involved in the rescue attempt. Move all vehicles away from the scene and do not allow vehicles entering the scene closer than 100 feet. Have outside traffic park at least 300 feet away from the scene and keep bystanders back 300 feet. Find and secure a responsible witness. Determine the number of victims in and out of the trench. If possible, also determine their location in the trench and their position at the time of the collapse. Determine length, width, and depth of the collapse. Determine how long ago the collapse occurred. Determine soil conditions. Check area for additional collapse potential. Cracks in soil, bulges in trenches, walls, location of soil pile, sources of vibration, etc. Check for other hazards, water, sewer, gas, electric, etc. Determine the risk to rescuers versus the time element. Will the victim be alive when the rescue is complete? Is there a chance for survival? Rescue guidelines. Notify police and fire departments immediately. Relay pertinent information from scene management to the authorities. Never enter a trench for a rescue that is more than 5 feet and unshoveled or unsloped. Never enter a trench for a rescue that is 4 feet deep and is unshored, unsloped, and in unstable soil. Planning ahead may save lives. Have shoring on site if you will be excavating 4 feet or more in depth and you will have people working in the trench. On large jobs, know where the shoring is so it can be brought into the site immediately. Remember, additional cave-in follows within minutes or seconds of the initial cave-in. Do not become a victim by jumping into the trench after the initial cave-in and before the trench is stabilized. If a victim is recovered in time, someone must be on site that is medically trained and able to assist the victim's condition and provide emergency response care to the victim until the paramedics arrive. If a victim becomes buried under 1 foot of soil or more, you have approximately 6 to 10 minutes to rescue the victim and restore breathing. With this in mind, you must ask yourself whether you're dealing with trench rescue or body recovery. This answer may affect your actions.